So in the last 2 weeks, we were mostly learning calculus, a very useful mathematical tool that we would be using in this course to study mechanics, motion of objects. And in this lesson, and then as we go along, now we would be focusing more on the mechanics problems, the situations that we want to study using the laws of mechanics, and we would be using some of the things that we have learned before. So I want to start with in mechanics we have two not very often and not very emphatically distinguished or emphasized branches of mechanics. One of them is, and we have already introduced ourselves to position, to speed, to acceleration. So these quantities in a way describe motion or quantify motion, and they also, then we have relationship between these quantities. So if we know one quantity, one of the two quantities, then we can find the third one. And when we don't worry about the causes of motion, where the motion, what is causing motion, what is an object to causing an object to move, if we disregard that, if we do not worry about that, if we do not ask that question and only look at the motion which is described by these physical quantities, such branch of mechanics is called kinematics. All right,
मैंने आपसे एक सवाल पूछना था।
जी बताएं।
वो जो आपने क्विक कैलकुलस की बुक अपलोड की थी, मैंने वो पढ़ी थी। उसके अंदर ना एंड के अंदर इंटीग्रेशन के अंदर था मल्टीपल इंटीग्रेशन। वो मेरा नहीं ख्याल वो आपने अभी तक पढ़ाया था। उसमें बेसिकली दो वेरिएबल्स के एक साथ इंटीग्रेट हो रहे थे।
ठीक है,
तो वो प्लीज आप मतलब करा देंगे वो मैकेनिक्स शुरू कराने से पहले, क्योंकि वो उस बुक में थे और अगर वो इंक्लूडेड होंगे हमारे क्विजेस वगैरह में तो वो प्लीज करा दें।
तो वो किस बुक में है?
सर जो आपने क्विक कैलकुलस अपलोड की थी ना, उसके अंदर इंटीग्रेशन के चैप्टर के ना एंड पे है मल्टीपल इंटीग्रेशन।
ठीक है, डोंट वरी अबाउट दैट येट। ओके,
चलो सर।
all right. So when we disregard what causes the motion, and you know that the force causes motion, and if we don't consider the force and just look at these quantities, that's kinematics. But if we, and later on in this course, we would be looking at the causes of motion, and then we will try to quantify the relationship between the quantity of the cause, which is force, and the quantity of motion that it produces. And that branch of mechanics is called dynamics. Please do not look, the classroom that I'm teaching in can barely seat 10 to 15 people. Once I announce the location, I know a lot of you would be here, and then that would be a logistical hassle, and the COVID response team would have to come and remove you from here because we would be violating SOPs. So please do not try to come in the class personally, okay? And I cannot treat 10 of you preferentially and allow you to sit in the class, and or two of you or five of you, and not allow the rest of the class. So please do not try to come personally. If you're so interested in talk to somebody, I don't know, maybe the dean, we do have an auditorium, but I don't know the capacity. So talk to them, and if they can arrange something. I personally enjoy teaching in person, so I'm all in favor. But that's not me. Okay, the class arrangement, the logistics is not my responsibility. Talk to the your OSA or whoever is responsible for this. Okay. So in this lesson and in a few more lessons afterwards, we would be only focusing on kinematics. Another very important assumption or approximation that we would be making in this course, majority of the instances, and then there would be some exceptions to it, that any object that we deal with, if it's even if it is a big object and its motion is as long as each point on that object is moving in the same fashion, there is no distinction between different points on an object, we can treat that object as a particle, as a point particle. So let's say, for example, if you have a rolling tire, all right? So if you have a tire that is rolling on flat surface. Now, if you look at this point, and if you look at this point, and if you look at this point, all these points are moving differently, all right? So such an object, we cannot treat it as a point particle, all right? However, if this object, if this tire was not rolling, but sliding, all right, then each point on this tire would be moving in a similar fashion, and we could treat this tire as a point particle. So when it really depends on the type of motion, when we can treat an object as a point particle, and when we cannot treat as it is as a point particle. So the finer distinction is that if an object has no internal motion, that can be, for example, rotation or vibration. Another example is, for example, a water molecule. So here you have oxygen, and then you have two hydrogens attached to it. All right. So if you have if you have hydrogen, now these distances, the distance between hydrogen and oxygen, and this distance, the distance between hydrogen, the other hydrogen and oxygen, and sometimes you call them bond lengths. These bond lengths are not fixed. So a hydrogen, a water molecule, the hydrogens and the oxygens are vibrating. So this hydrogen changes its position. It vibrates, oscillates back and forth towards oxygen. Same is the case with this object. So the whole water molecule, although it's a tiny object, we cannot treat it as a point particle. Okay. So because it has internal motion, similarly, a rolling wheel has a rotational motion. A water molecule has vibrational motion. All right. So in some circumstances, if even when they have internal motion, we can treat them as point particles, but you have to be very careful in making that assumption. But most of the cases that we would be dealing with in at least the first part of the course, we would be making this approximation very often. Doesn't matter how big an object is, even a human being or a cat or a football, whatever object we have, we would literally treat it as if it was a point particle, as if it was a dot in the space, as if it was an electron. Okay. So this is what we call the point particle approximation, but we would be making it very carefully. Okay, so let's say we have a particle, and now a particle can speed up, it can slow down, it can stop, it can even reverse motion. The reverse motion example is if you throw something, an object up in the air, it travels in this direction upwards first, and then at some point it comes to rest, and then again starts falling down. So this is an example of reversing motion. So in the last few lessons we did also develop the equations of motion, which let me just write here. All right, so these are the equations of motion, and and you remember that we can apply these equations of motion only when we have a constant acceleration. And if I want to use the language of calculus to express that acceleration is constant, so the time derivative of acceleration would be zero, would be a constant, or zero. No, that would be zero because a is constant. So that means the acceleration is constant. Whenever we have this situation, then we can apply the equations of motion. First, we want to apply this to a particular example to study and understand various important concepts. And towards the end of the lecture, I would try to generalize this concept. So what happens when we have acceleration which is not constant? So that situation, then these equations cannot be applied, and then we need to have something more general than that. So I've tried to generalize this towards the end of the lesson. Now let's say that we have a platform that is 15-meter high, and then we have someone doing an experiment from the top of a 15-meter high platform. And what we do is we throw an object, let's say a rock or something else, upwards. And of course, if you throw it upwards after reaching certain height, it would fall down, and it would fall down all the way to ground. नहीं यार, आपको बताया तो है कि ना है क्लास में, अब मैं आपको बिठा दूं फिर क्या, बाकी लोगों का क्या कसूर है? बैठ जाएं अभी, लेकिन नॉट अगेन। आ जाए, बैठ जाएं, बंद कर दें दरवाजा। All right, so the object falls down. Now we have to describe its motion. The first thing that we specify is the moment this object is released by this experimenter, we take that moment in time to be zero. All right. We also know, because we are doing this experiment, that at the moment of release of this object upwards, its initial velocity, or u in our equations of motion, is 10 meters per second. All right. Okay, now we want to ask several questions and then try to answer those questions about the motion of this object. For example, we want to find out the height that this would attain before it reverses its motion, the height that it acquires, this object. So we want to find out this point in X. We in general want to find out its position as a function of time. That would be really nice to know. We also find out the time it would take from the release, getting to the maximum height, and then again hitting the ground. All right. So we want to find out the time, for example, first to reach the maximum, to acquire this height. So that would be a point in time. So I could just write it as t, or I could just say it th, or whatever notation does not really matter. I could call it t1, or I could just leave it as t. Okay, but I also want to find out the time that it would take to hit the ground. So these are the type of questions that we want to ask and answer about this particular situation. All right.
सर ये xt क्या क्वेश्चन है?
We want to find out the position as a function of time for this object.
ओके सर.
सर आप दोबारा बता देंगे कि TH, T1 और T2 किसको रिप्रेजेंट करता है?
लेकिन ये किसी को भी नहीं रिप्रेजेंट करता, और इन अदर वर्ड्स इट रिप्रेजेंट्स अ मोमेंट इन टाइम, अ पॉइंट इन टाइम. ठीक है ना? देयर कैन बी सेवरल पॉइंट्स इन टाइम. ठीक है. एक पॉइंट इन टाइम दैट वी कुड बी इंटरेस्टेड इन एंड इज मीनिंगफुल इज दैट how much time would it take to get to the maximum height. Okay, so that would be a point in time. You could call it t1, you could call it t star, whatever you like. And then there is another point in time that we are interested in, or interval in time if you like. Okay. When it would hit the ground, so there would be another time, and I could just call it t, or I could call it t1, or I could call it t star. It doesn't really make much difference. The only thing that you have to be aware of is that there is a running time. That is our variable here, t. There is a running time. Once we start at 0 time, then the clock is running, and the position of the object as a function of time is changing. Its speed is changing. Its acceleration is not changing. That's a given, because we are considering motion under free fall, and I'm going to use the equations of motion that we know. If g was changing, I wouldn't be able to do that. All right.
All right, sir. Thank you.
So the difference is a running time, the variable, and a point in time. Now, since we have this situation, now we have to choose now a coordinate system. Okay. And usually if you are considering motion in one dimension, and the object is not reversing its motion, that the coordinate system doesn't serve much purpose, and we usually do not worry about it. We start solving the equations of motion. That's probably what you have been doing in your school. But when we have two objects, an example that we saw in the recitation, where we had two objects moving in opposite direction, if you have a situation like that, or if you have a situation where an object reverses its motion midway, okay, in those situations we have to be careful, and to get the correct answers we need to choose a coordinate system. So in this case, it is still motion in one dimension. There is no second variable, there is no second direction yet, so we just need one axis. I can choose this axis to be pointing upwards. It means that as an object, as x, as object moves up, its x increases, its position increases. So I can set 0 on this side, so this is the positive direction of the axis. But I could also choose this axis in the other way around. I could have chosen the axis to be like this, and I will do so towards the end of this example to make a very important point. But for the time being, let's keep the axis in such a way that the upwards is the positive direction of the axis. then we have to choose a 0. And this choice is absolutely arbitrary. It really depends on our mood, okay, or convenience. If you do not choose carefully your coordinate system, it may complicate the process that you need to do to get the correct answer. All right. But the physics does not depend on the choice of the axis. Whatever axis you choose, if you're careful and consistent, you will still get an answer. But a bad choice of coordinate system may complicate the process that leads to the right answer. All right. So this is the height of the platform, 15 meters. I could set the 0 here at the ground level. Not a very bad choice, but I could also set the 0 at the maximum height. All right. And another reasonable choice. But let's start with 0 at the ground level. So if an object is, if the value of xt, in other words, is 0, that means the object is on ground. So now, since we have chosen the coordinate system, can you tell me now, we have already specified some quantities, that the initial speed is 10 meter per second, the start time, we set the clock to 0. And then we have, what other quantities we have? Yes, so we have the acceleration that this object would be subjected to. All right. And then now what would be the initial position of this object in this coordinate system?
15.
15 meters. Bas, thank you. 15 meters. So that would be the initial position. And what would be the position of this object when it hits the ground? 0, right? So in a way, we know its final position, if I may denote it with F. So again, he's x0, initial position, xf, final position. These are points in space, while x itself, this x, that's a running variable. That's the position that continues to change, right? So xf would be 0 meters, all right? Although we are going to, so one more important point before I move on here. So when now in this coordinate system, if a physical quantity turns with the negative sign, it means is decreasing, is pointing in this direction, okay? And when it is positive, that means the position of that quantity is on the positive x-axis. So it could, for example, now my position is positive in this direction, 0 here and 15 meters initial position, all right? But what about the acceleration, the gravitational acceleration g now? You're often confused about the sign of g. The sign of g is really determined once you choose the coordinate system. Now this is dictated by the nature of gravity, by the nature of force behind this quantity. It is always pointing towards the center of Earth, okay? But it can be positive and negative. So the gravity does not subscribe to the sign of negative or positive. So the gravity says this much acceleration would be an object at the surface of or close to the surface of Earth. This much acceleration it would experience, which comes from the force of gravity. The negative sign in G, around G, appears once you set the coordinate system. In this case, the coordinate system is that the positive x-axis in the upwards direction, while G points downwards, always downwards. So in our frame now, G would be negative. G would be negative. But if I had chosen the x-axis of my coordinate system pointing downwards, the positive x-axis downwards, then G would have been positive. And both cases would lead to correct and same answer.
सर आपने x एक्सिस को ऊपर की तरफ क्यों लिया?
Just a convention because I'm feeling like that today. Tomorrow I may take it downwards. And that's a serious answer, by the way. There is no real reason for me to assume x-axis upwards. All right. I could have taken x-axis in any direction, not upwards and downwards. But in that case, the motion would have become two-dimensional. I would need two axes to describe it, and the problem would become complicated.
सर ये साइन ऑफ जी का रिलेशन विद एक्स एक्सिस आप फिर से समझा सकते हैं जरा?
किस चीज का?
सर साइन ऑफ जी का।
देखें एक्स एक्सिस है, ये पॉजिटिव एक्स एक्सिस है। ठीक है, ठीक है ना?
ठीक है सर।
और आपको ये पता है कि जो ग्रेविटेशनल एक्सेलरेशन है उसकी डायरेक्शन इज ऑलवेज पॉइंटेड टुवर्ड्स द सेंटर ऑफ अर्थ, वो इस तरफ है। ठीक है, तो व्हेन योर कोऑर्डिनेट सिस्टम्स पॉजिटिव एक्सिस एंड जी which always points downwards are opposite to each other, then G is negative.
हाँ सही हो गया सर।
And when you choose an x-axis that is pointing downwards, then the G would be positive. Okay.
सर ये G का यूनिट मीटर्स पर सेकंड स्क्वायर होगा ना?
जी जी जी, थैंक यू।
Sir, I had a question.
जी जी।
Sir, I was going to ask, isn't G का sign relative to the direction of velocity?
Yes.
So
It is not related to the direction of the velocity. It is related to the rate of change of velocity.
Okay, so can't we think of it like this? If velocity is, if for example, an object is going upwards, the direction vector of the velocity component is upwards. And if acceleration always points downwards, that means the acceleration would be negative.
Yes, but then in that case, the velocity would be decreasing.
Yeah. Okay.
ठीक है। So even before solving, and we would get the actual functional dependence of x of t. Eventually, we would get this curve, we would get this function. But even before that, if we just look at the extreme conditions, the extremas, the initial conditions and the final conditions, we can have a guess of how the velocity, the position time graph would look like. So this is very important. What is the position at t equal to 0? 15 meters. ठीक. And what would be the position at when it hits the ground at some time? What would be the value of x? Zero. All right. But since we are throwing it upwards, what would be the position immediately after we have thrown it? Somewhere here, upwards, right?
Slightly above.
Right?
Yes.
So it would, in all likelihood, make a graph that looks like this. Now, of course, I'm cheating because I know it's parabola from my earlier knowledge. But so I wouldn't be able to guess that it's a parabola without knowing beforehand. But I would still be able to make these inferences. This point, a point higher than this point, and then hitting the ground. All right. So it seems that the object goes up, reaches a maximum height at this point, and then it starts dropping down. Now we will try to find out, so the equation, so we will try to find out the maximum height that it requires, the time it takes to get to that height, And the equation that we need to work with or start with is this. The time rate of change of velocity or speed is equal to minus g in our coordinate system. You have to be careful. Now we have fixed the coordinate system. Once you choose a coordinate system, then you have to be consistent. So this is the equation of motion that we need to solve to get some meaningful quantities. So for example, if I can find v from this equation, and which I can and which we can, we have learned it by using the antiderivative or the integral, then we would have found its instantaneous velocity. And from its instantaneous velocity, if I could find v of t, then I could do another integration, because v of t is nothing but the time rate of change of position. Then I can do another integration and find out x of t. All right. So we can.
dv over so ये dv over dt equals minus g सिर्फ तब के लिए वैलिड है ना जब तक वो मैक्सिमम हाइट पे पहुंचे, कि माइनस g तो सिर्फ ऊपर की डायरेक्शन तक है, जब रहेगा तो फिर सिर्फ g नहीं होगा पॉजिटिव वाला.
No, you don't need to change the sign now. Okay. So yeah, Alan, we will see you. Let me complete this example. ये g अब minus ही रहेगा, because it's always pointing downwards and my coordinate system is fixed upwards. So doesn't matter. That's the benefit of the coordinate system. वो जो g आप change करते हैं ना high school में, ऊपर जा रहा है तो ये कर दें, नीचे जा, because you don't have a coordinate system. Okay. And or I don't know why you do that. So you choose a coordinate system and you set g to minus g, and that's it. And you will see it works out. All right. Now, and now we know from our calculus that v of t would be simply 0 to t g dt. All right. So I'm just using the integral to find v of t. All right. And the integration is nearly trivial. It is simply gt, right? And a constant of integration u. Okay. And then you can find out that the constant of integration would be nothing but the initial velocity. And I am feeling uncomfortable about the constant of integration. At the same time, I have limits on my integral. All right. And this integral, although it looks like a definite integral, it's not a definite integral because t is not defined. It's an indefinite integral. This is just a nice way of writing it. All right. So it's still an indefinite integral, and I still need a constant of integration. Okay. And you can find that out if you set t0 in this equation. Then at time 0, the v of t would be equal to u. That's our initial velocity. So we got this equation of motion in our particular case. Now this is the only difference in this equation of motion and the equation of motion that I wrote on the board before. The general one was a positive sign here, because that's written in the most general terms. And now we have specified our coordinate system. And in that coordinate system, the acceleration is negative. And if you're not sure about the solution, you can always take the derivative of this quantity here, and then you would get this back, the equation. That's the proof that this integration is correct. Now you can take again dx over dt is nothing but the velocity, which is u minus gt. And now you can do the integration yourself. I'm not going to do it. I'm going to just write the answer with a constant of integration. The answer would be ठीक है. So now we have found x of t, the position as a function of time and the velocity as a function of time. And we are already given the acceleration, which is a constant. So now I'm interested in finding out the time this object would take. Let me make another figure because that's on a different board. So I'm interested in finding out the time that it would take to reach the maximum height after release. So how do I impose that condition on my equations here or here or here? These are the equations that I have. This one, and this one. So how do I impose that? How do I make sure that the time that I would be calculating is when the object is actually at that height? Any guesses?
Their velocity 0 हो जाएगी.
जी, बिल्कुल, very good. So you see, when the object is released, it has an initial speed or velocity of 10 meters per second. But as it goes up, remember, this term is negative here. The acceleration is downwards. The initial velocity is upwards. And it's just given velocity. This is not increasing, it's constant. Okay. But as time goes, this term is linearly growing up. At some point, these two terms would become equal and the velocity would be 0. That is the physical condition I can impose to find out the time to reach the maximum height. So u minus gt, and now I can plug in the numerical values to get an answer. So this is 10 meters per second. This is 10 meters per second, and the t. So what is the value of t here then? 1 second.
1.
This is how much time this object would take to get to the maximum height. Because when it reaches the maximum height, its velocity is 0. And that is the condition we are imposing.
सर ये x 0 क्यों है?
जी?
आपने x 0 लिया है?
नहीं, velocity 0 ली है इस equation में.
ओके सर, थैंक यू.
ठीक? All right. So now we want to find the position, this actual position. And now that's easy once because we know time. All right. If you look at this equation, that gives us the position, right, as a function of time. And if you look carefully, we know all the quantities that we need to find that out. We know the initial velocity, we know time, okay, we know the acceleration, and we know the initial position. All right. And somebody was asking what was t1 and what is t. So this is t1, a specific moment in time. When the clock hits 1 second, by then the object has reached the maximum height. Right. And now we want to find out the maximum height or the position at the maximum height. And it's very simple. Just substitute all the values that you know in this equation. I'll let you do the numerics. That's 10 meters per second time 1 minus half time 1 square 1 plus 15 meters. And here it would be
20.
meters per second squares. And the x at, remember, this is the proper way to write if you want to be careful. X at t equal to 1 is
20.
20 meters. How much distance it has traveled after release?
5 meters.
5
5
meters.
meters.
That's the absolute position in our coordinate system from 0. So it was already at 15 meters and it has only traveled 5 meters up before coming to rest. All right.
Sir, when answering questions, हम बताना पड़ेगा कि हम लोग absolute वाली की बात कर रहे हैं या फिर relative वाली की बात कर रहे हैं.
जी जी, क्या क्या बता रहे हैं? क्या क्या
Sir,
सवाल है
जब
आपका?
हम लोग questions answer कर रहे होंगे, हमें specify करना होगा कि are we talking about the absolute distance above the ground या फिर the relative distance from that particular point जहाँ से object launch हुआ था.
Yeah, once you know that, then and then if you're, I mean, it should be clear from your context. I mean, I don't know how to answer that question. It's a hypothetical question. के absolute distance करना है या usually if you are asked x as a function of time, then it should be with respect to the origin, with respect to the coordinate system in absolute terms. Okay, but then after asking the question, if there is another sub part of that problem that asks you how much distance it has traveled after release, then of course you're smart enough to know that and subtract 15 from here.
All right, sir. Thank you.
Excuse me, sir.
जी.
Sir, वो जो launch वाली initial velocity है u, वो किसी angle पे होगी या like सीधे ऊपर फेंक
नहीं नहीं
देंगे
नहीं
हम?
नहीं ये मोशन इन वन डायमेंशन है, सीधा ऊपर फेंक रहे हैं. ये तो ऐसे बनाया कि वो सर पे ना लगे आके वापस. ठीक है.
Okay.
I have a very quick question to all of you. You don't need to unmute and answer. You could answer in the chat or just answer in your head. I'd know. If we shoot a bullet from a gun absolutely vertically. Now, when a bullet is released from a gun, I don't know the speed, but I think it's in the range of, it's close to the speed of sound, several hundred meters per second, right? That's the typical speed of bullet. So, and God forbid if it hits a living being, it kills them because of its momentum, right? Now the question is, we have this culture in Pakistan where people shoot in the air whenever there is a reason to do that, or absolutely no reason to do that. And so the question is, let's say that you shoot a bullet right straight up in the air, and it is traveling, assume 300 meters per second. What would be its speed if, God forbid, it comes back and hits in the head of the person who shot? What would be the speed of the bullet? 10 meters per second. Anyone else? 10 meters per second.
If there is no term, if there is no air resistance, then it would be the same speed that it left from the gun.
Excellent. Very good. Yes, it would be the same speed. So that is, I wanted to make this point that you understand it's extremely dangerous to fire in air, because it is as if you were going at that, if you're just rising up a few meters and shooting downwards right into people's heads. Okay, because the initial speed of the bullet going in the air, when the bullet drops down, it drops with the same speed and is as lethal. And you can, by the way, show it using these equations. That's the beauty of mechanics. Okay, so the next question that we have is that the time that this object takes to hit the ground. So what would be the time when it hits the ground? So how do I find that? Any guesses? Just in the chat would be good. Set x to 0. Yes. So the physical condition is that in our frame of reference, when the object hits ground, its x would be 0. So I'd set x equal to 0 in this equation. All right. And now I can plug in the numerical values as well. 10 meters per second. I'm just omitting units for the time being. You're allowed to omit units while in the equation, but final answers should never be left orphan of units. That's a grave mistake. All right, so this is the equation. If I could just simplify this term here, that's half g, that's 5. And 5 is common, can just divide the whole equation with 5. This would be 2t with minus 5, let's say, because I like the equation to look like this. Minus 3, right? Do you recognize this equation? Just if you recognize, type in your chats. What is this equation? What is this equation? Yes. Quadratic equation. And you all know how to solve a quadratic equation, right? So
सर ये आपने -2 के साथ क्यों लगाया हुआ है?
मैंने -5 से डिवाइड कर दिया सारी इक्वेशन को.
तो सर +2 और -t² नहीं होना चाहिए था?
क्या?
सर ने -5 से डिवाइड किया. 5
अच्छा, -5 से डिवाइड किया. ओके हो गया, फिर तो सही है.
ठीक है. So now I would have two answers for t. T equals to -1 second. If you can't solve, these are the factors. 3 plus 1 times t squared minus 3. Oh, sorry, no square. T minus 3 equals 0. All right. And there would be another answer. And that is 3 seconds. Right. For the time being, forget about this, the negative time. Just focus on positive time, and then we'll talk about negative time in a minute. All right. Well, I mean, there is nothing really that we need to know more. I mean, that was the question, that the time it takes to hit the ground. So it takes total 3 seconds to hit the ground. And of that 3 seconds, 1 second it takes to reach the maximum height, and then 2 seconds to drop from the maximum height to the ground. Okay, now let's talk about the t equal to -1 second. Remember the way we set the clock. So we set the clock at the beginning of our observation or the experiment equal to the. So we set the clock t equal to 0 when we start the experiment and the object hits ground at t equals to 3 seconds. So this is the time interval that our experiment or our observation is confined to. So any time that is larger than 3 seconds, of course, is of no interest to us because the object has fallen on the ground and that's it. So nothing happens. Any time before t is outside the window of the observation. So time here is minus, and it's fine because we chose the t equal to 0 quite arbitrarily. So if I had chosen that when I throw the object into the air, that time when my clock was showing 1 second, then this root would not be negative. This would be 0. Okay, so the negative time is fine, no worries. It is just that it is outside the window of our observation. Okay, but it gets more interesting.
Sir, why did you change the signs of the equation?
Don't change the sign of the equation and solve it. You'll get the same answer. A bad choice. No, I mean, it doesn't make a difference if you solve the equation. If you're comfortable doing it right away, I don't know. I thought I was going to factor it myself, and that's why I changed. But you really don't need to do it. The roots would be the same.
So one question.
जी.
Sir, इसमें 0 is the final velocity v, right?
जी.
जो हमने 0 लिखा हुआ है वो v की वैल्यू 0 assume किया हुआ है।
कहाँ पे 0 लिखा हुआ है?
जो equal to के इस तरफ लिखा होगा।
ये फाइनल पोजीशन लिखी हुई है, ये वाली इक्वेशन है, ये वाली, ये देखें ना, this equation here, ये x को 0 लिखा हुआ है।
ठीक हो गया सर, समझ आ गया।
Okay, but let's say that let's try to find the position of the object at t equal to -1 second. Let's do that. You can do it, but I'm just going to write the answer right away. If you substitute t equals to -1 in the equation, x of t, and if you carefully do the manipulation, that the answer you would get is 0. X of the position at t -1 is 0. All right. Then you can calculate velocity at t equal to -1. And just you have to substitute the value of t in the equation. And the answer that you will get is 20 meters per second. Now, although both of these quantities are outside the window of our observation, but if I could bring down the figure, the equation of motion is telling us that it doesn't really know that we held the object here and threw it from this position. If you propagate the equation of motion backwards, it tells us that as if it would be the same, the rest of the problem would look same if we had thrown this object from ground with 20 meters per second upwards. It would have reached 15-meter height with 10 meters per second speed. The same initial conditions as if, so it really does not understand where the experiment started, okay, or where the observation started, and it doesn't really regard that there is somebody standing here throwing it up. So it is in a way going back in time and seeing where the object was in the past. Now we are not taking initial values, we are calculating them from x, from that function, from this function here. You substitute -t, okay? And here, of course, you substitute the initial conditions, the u and the x, sorry, do you have? No, because yeah, you just substitute time in it and whatever quantities you know, and then you will get the position 0 at t minus. G? G. No, 15 is the position. You would plug in 15 You would plug in the acceleration and you would plug in the initial velocity that we have at this time. And then negative sign would take care of that these are initial conditions going back. The initial conditions remain same. The minus sign in the t would make sure that these are the starting point. That's where we are absolutely sure about a few things, position and the initial velocity. And minus t would guarantee to propagate in this way back in time, and positive t would guarantee to propagate in the forward direction. All right.
So sir, it projects the trajectory of the object in the past. So sir, excuse this equation, it projects the trajectory of the projectile.
Yes. So this is the trajectory of the object. It's not really, it's just a motion in straight line. Okay. So there is no second dimension. And this X predicts the motion, the trajectory. And it's not limited to future or present. It is also, you can, for example, if an object is traveling before you and you can record successfully its motion, its trajectory, you can not just predict its future trajectory, you can also reconstruct its past trajectory.
So yes, sir.
And this is what is called Newtonian determinism, Newtonian mechanics. So this mechanics that we are studying, thanks to Newton, also referred as classical mechanics. And it has the capability that once you solve the equations of motion successfully, then you cannot just tell with 100% certainty the future trajectory of an object, but also its past trajectory. And sometimes you would learn in modern physics, this was referred to as Newtonian determinism. And of course, it does not hold because it's fine in the macroscopic universe, but once you go to microscopic universe, once you have to deal with subatomic particles, we cannot predict the future or the past trajectory of a particle with 100% certainty. And that's why we needed a new theory now called quantum theory or quantum mechanics. Okay.
सर ये आपने t-1 कौन सी इक्वेशन में डाला था?
इसमें डाला था, यहाँ पे.
और सर इसमें x क्या था?
x इसमें था, x तो फाइंड करना है, x तो फाइंड किया है.
ओके सर, ओके, थैंक यू.
x नॉट वही है जो यहाँ पे है, जो हमारा पॉइंट ऑफ ऑब्जर्वेशन है t0 पे. x नॉट यही हमारी इनिशियल कंडीशंस हैं, गोइंग बैकवर्ड्स एंड गोइंग फॉरवर्ड्स. And now you see, we did not change the sign of G going upwards, going backwards, going even backwards in time. All the signs are consistent. Okay, something I said about the choice of a coordinate system. So I'm not going to work out all the numerics, but let's say that we invert the x-axis, okay? We choose a coordinate system with a positive x-axis pointing downwards. Now the first thing is, now the acceleration would be dv dt equal to plus g, all right? Now the initial speed, when you release the object in this direction, that would become negative, minus 10 meters per second. All right. And again, I can choose I can choose the x0, x equal to 0 at the position of release. Okay. So let's say this is the position of release. Okay. And we set it equal to 0. And this is 15 meters above the ground. Okay, now this 15 meters still remains positive because I set my 0 here at the height, and then to get to the earth you need 15 meters. Any distance above this point would be minus. It now rises up to -5 meters above the, okay, so x naught would be still 15 meters per second, and of course I turn on the clock right at the time when I start the observation. Now if you substitute, please mute your microphone. Now if you substitute these into the equations carefully, first you need to solve this equation instead of the one with -g, and then you substitute all these values. The numbers you would get, for example, the time it takes to reach the maximum height would still turn out to be 1 second. And the distance it needs to hit the ground would be 3 seconds. All right, you can verify, and the acceleration now would be positive. The important point is the acceleration g would be simply 10 meters per second. Both ways, when the object goes up and down, acceleration stays positive. The sign of the acceleration depends on the choice of the coordinate system, not on the direction of motion.
Sir,
जी
x naught 0 नहीं होगा सर?
जी sorry yes, x naught 0. Yes, thank you. ठीक है, thank you, rightly spotted. So this is a very important result, and it's very important that you understand it, that physics does not depend on the choice of coordinate system. Physics does not depend on the observers. Okay, and that is the but here is something more. In Newtonian mechanics or in classical mechanics, the time intervals do not depend on the observer. So it does not matter who is and where are you observing it from, or which frame of reference you are measuring time. The time intervals are absolute. Okay, this is another aspect and a very important aspect of Newtonian mechanics. The first one that I talked about, Newtonian determinism, that you can determine or predict the trajectory in past or in future with 100% certainty, but it fails at microscopic scale, and we need a new theory, quantum theory. Newton's mechanics also implies that time intervals are independent of the frame of reference. Okay? And it works fine as long as we do not travel very fast. As long as we do not travel very fast. Okay, this is true. And this is sometimes referred as Newtonian absolutism. The time in Newton's mechanics, in classical mechanics, is absolute. Later on, Einstein realized that when you go at very fast speeds, it is more important to preserve the laws of physics, to keep the laws of physics invariant to different observers. The laws of physics should be same for different observers. But once you impose that condition, the time could not be absolute. So that's the basis of the Einstein's special relativity, which challenges Newton's absolutism. The time is no more absolute. The laws of physics still remain invariant to different observers. Okay, so this was another failure of the classical mechanics, and that gave birth to relativity. Oh, sorry, मैंने उसको origin यहाँ पे लिया है. नहीं, अब तो ये हाइट 0 है. ठीक है, अब ग्राउंड पे उसकी पोजीशन, फाइनल पोजीशन x = 15 होगी. Okay, questions at the end, please hold. Let me finish the non-uniform acceleration, and then I'll answer your questions. Okay, now we have a case of non-constant acceleration. Or if you want to express mathematically, when you have the situation dA by dt not equal to 0, and we had this situation, we had a curve in one of our recitations where, although we did not do this type of analysis there, but we started with x of t, and x of t was proportional to a polynomial whose largest degree was t cubed. So two derivatives, dx of dt and another times the double derivative of dx of dt still had time dependence. So acceleration was time dependent. There are situations in our life in mechanics where acceleration is not constant, it's changing. And if that is the case, all the equations of motions that we have studied so far, they are invalid, or they are the special case of a more general equation of motion that we are trying to deduce. That's a special case where acceleration is constant, then those equations work, they're simpler. But when the acceleration is not constant, then we cannot use those simpler equations. We need to use something more general. That is the concept. Again, we start with this equation, time rate of change of speed or velocity. We're not making this distinction just yet because we haven't introduced motion in more than one dimension, and we haven't introduced vectors yet. But from the next lesson, hopefully we would start learning vectors. If you have this situation, then you cannot solve if A is not constant, then you cannot just use the equation, and you have to do proper integration. Okay, can I write this equation like this? I just take the dt on the other side, and that's perfectly fine. Okay, and once I do that, then I can do the integration on both sides from some initial time t naught, okay, to a some final time t. And then here again, I do the integration from some initial time t naught to a final time t. And you can always actually take the initial time to be 0. All right. So look at this equation carefully. This integral would be v evaluated at 0 and evaluated at t. Sorry, this is a mistake. I'm really sorry. That's very bad. So this integral is not over time. I'm sorry. This integral is over velocity. So I have some, let's say I have some velocity v at t equal to 0. I take it as v, which you call u, for example, and a final velocity at t equals to t. Some indefinite moment, some undefined moment, some unspecified moment in time. Okay, and this of course is on this integration is over time. Okay, now this would be simply v at t equal to 0. What is v at t equal to 0? The initial velocity, right? So this is u and this is v at t equals, and on this side I don't know the functional dependence of acceleration on time, so I cannot do the integration. I'll just write it as such. A is a function of time. All right. And this turns out to be V of t minus u. This is a definite integral equals 0 to t a of t dt. All right. And then you can just take this term on the other side, and the equation looks like u plus 0 to t. Okay. So for a non-uniform acceleration case, this is the most general equation of motion that we would be dealing with. Because in the simple case here, for example, when acceleration is constant, it means acceleration has some constant value on this axis. Okay, this is at, right? And here we have time. And the velocity is nothing but area under the curve up to time t on this axis. So it's trivial finding a constant. We just multiply the acceleration with time, and it gives us the exact answer, the area under the curve, which is the velocity. And from there, we get the equation v equals u plus at. But if acceleration has this dependence on time, this type of dependence, let's say this type of dependence now, you see this? A of t and time. Now we cannot simply multiply the acceleration with time and expect to get this area under the curve. The only correct way to get this area under the curve is to actually integrate this function. Okay, that's the origin. And you can always get this equation, the one that is valid for acceleration valid for constant acceleration. You can always derive this equation from this. Just take a to be constant, a would be outside, and the integral of the rest would be, integral of the one would be t. So you can get this equation from here, but not the other way around. This is the most general form, most general description for motion with variable acceleration. Okay, with this, thank you very much. That's all for today. I have uploaded another glow script code to the two programs that you already had. You're welcome to explore it. And if you have questions, please post them in Piazza or bring them to office hours.
Excuse me, sir.
Now I would take all your questions.